Hi, everybody. I want to continue on with our discussion of analyzing motion at a constant rate. The previous tutorial, we looked at graphical interpretation. We established some very important things that are going to carry forward again and again. So I put up here a generic position versus time graph for some object. It could be the truck, it could be the VW. It doesn't really matter. And what we want to do now is take this interpretation and translate it to algebraic equations, because the algebraic equations are quite versatile. I will point out in your reference tables what you have to know eventually, but for right now I want you to just focus on the three boxes I put here for the problems that are going to follow that I'm going to do, and then you're going to have to do it for your practice. Okay, so the key thing we established in the previous tutorial is that if I'm looking at this graph and I find a slope, the slope will give me some number, but that it's not just some random number. It represents something about the motion, and we said it represents the velocity v. Okay, so what I want to do is I want to translate that into an equation. And this is how we do it. We just use the generic y equals mx plus b. And we just use what we have here. So in this case, I'll just switch to a different color. Okay, what is our y value? Well, it's x. So x is our generic position. Where am I at any given time? That's equal to the slope. What does the slope represent? It equals the velocity. Okay, now here is something that I'm going to make a little bit of a tweak with for reasons we'll talk about later. I'm going to put a average velocity. Okay, so that bar is a mathematical way of saying average. So now our x variable is t, so that's v times t, and then plus our b. What is b? Our y-intercept. So our y-intercept could be 0, but it doesn't have to be. What does it represent? Well, it represents x naught. All right, and that little 0 stands for naught. That's, I guess, a British term. Okay, in other words, it stands for where we started at time 0. You don't always have to be starting at position 0. You could be starting ahead of something if there's a race. So that tells you where you are at any given time, where the average velocity v comes from the slope. For we see graphs that are not for graphs that are nonlinear, which we're soon going to see, it's important that we look at average velocity rather than a velocity at any given time. Okay, so this leads to an equation for the average velocity, which is really just comes from the slope. The average velocity, again, v bar, is equal to simply your change in time or change in position over time, the rate of change of position. We defined that previously. So that's the mathematical expression of that. But again, it's that v bar that's important. That's different than v for reasons in discussion we will talk about later. And then lastly, we can rearrange and solve for how much time it takes to do something. So taking this equation, rearranging, we see that the time it takes to go from one place to another is simply your change in position, all divided by how fast you're going on average. Now, let me just talk about delta x. Remember, delta x, by definition, is our final position minus our initial position. So even if I look at this equation here and I move the x naught to the other side, I see that my change in position equals my average velocity times time. Okay, so that's another way you can write that. So let's just do some quick examples. I know you can figure these out without these equations, but I expect you to see these equations written down. Okay, that's super important for reasons that we'll see later when things become more complicated. So don't just do these in your head or write down an answer that you get from a calculator. Show me how you get it. I don't want to see the proportions from math. That's not how it works. So this is how you go about doing it. So let's say we got information right here. So from lab, the tracker is rolled for 9 seconds. I'm going to label that as a t. So I'm just start labeling everything in terms of what they represent. This is super important. How far? So that's x. Okay, so that's my question mark. Would it travel in this time? Okay, well, we need information. So we're assuming something about the speed of the tractor. So let's put down from the speed of the tractor, right, the average speed, and it was constant, is, I think we settled on, darn it, I can't remember from the previous tutorial. Yeah, I think we set it on 20 centimeters per second, so I'm going to go with that. Even if I'm wrong, it doesn't really matter for illustrated purposes. So that's our average speed. So I want to know how much time, how far we go. So I'd want you to put, as per this equation here, x, where we start with, equals average velocity times time plus x naught. Now I substitute in the numbers. So I'm going to put in 20 centimeters per second, get in the habit of putting units, times the time, 9.0 seconds, plus 0, since our initial position is assumed to be 0. I don't need to put plus 0, so that equals 180. You see that the centimeters per second times seconds, the seconds cancel out, leaving me with a distance unit, as it should. So it's 180 centimeters. Okay, pretty straightforward. Again, I know you don't have to go through all this to figure that out, but I need to see it because when problems get more complex, you need a process, and this is the beginnings of our understanding of the process. Next question, how much time to go a total distance of 200 centimeters? Okay, so I'm looking for time. I can use any one of these equations. They're all really the same equation, just written differently, but I might as well go directly from that one. So I can say time is change in position over average velocity. So my change in position is 200 centimeters divided by 20 centimeters per second, and that of course is going to be 10. You can convince yourself centimeters divided by centimeters per second gives you time of seconds. You should work that out. Okay, and then what would be its speed then? Well, the temptation is to go with, well, let's calculate speed with this. But we don't have to because we know that it's moving with a graph that looks like that, and the slope is constant, and the slope is the same as speed, so the speed is still going to be 20 centimeters per second. We don't have to show any work from that because that comes directly from the graph or indirectly. All right, at this point, and I'm getting a little ahead of myself because there's another lesson we got to learn to help make this more sense, but I'll introduce it here anyway. You hear the term speed and you hear the term velocity. They're very similar, but there is a subtle difference. Okay, so one difference is speed does not have direction associated with it. When you're in a car and you the speedometer does not tell you if you're moving north, south, east, or west. Velocity, on the other hand, has direction associated with it. So mathematically, that alters the equation slightly. So average speed for any trip, whether it's one segment to that trip or 30 segments to that trip, is defined as total distance divided by the time it takes, the total time. Okay, so it's kind of like that delta x over t we had above, average speed. So how would you calculate velocity? Velocity is very similar, but it's a subtle difference. It's total, well, I shouldn't even say total, that's redundant. So it's just displacement. We haven't formally defined displacement yet. Okay, I'll give you an example now, but there will be a tutorial that explains it later. So it's displacement divided by time. And so implicit in that is displacement has something about direction built into it where distance does not. Again, on a car, an odometer, it doesn't tell you what direction you were traveling if you roll off, 10 miles. Displacement does tell you something about direction. So let's just do a quick example. And if you're still a little bit confused with that, when we do enough practice, we'll start seeing the difference. So we got a car travels 10 meters and south, so that direction is coming into play. It stops, turns around, and goes back to the original position. Okay, in other words, where it started from. This all took 20 seconds. So I'm going to ask you, what's the average speed? So average speed, so in terms of writing an equation, v bar is delta x over t. Now, for velocity, speed and velocity is hard to distinguish with just a v. Technically, speed is a v with an absolute value sign over it. And then velocity is just a v by itself. I'm not going to really worry about that right now. We'll just talk about speed versus velocity. So if I use the equation up here, what's my total distance traveled if we went and then turned around? Well, it's 10 plus 10. 10 there, 10 back. Took 20 seconds, and so that is 1 meter per second, I believe, right? Okay, pretty straightforward. Displacement, again, so if I ask for average velocity, I want displacement divided by time. Well, displacement is simply how far you are from where you started. So we traveled 10, we came around and finished there. Here's my start, here's my end. How far away am I? Well, I'm 0. So x, not the absolute value, but the displacement vector, I'll put a little arrow above it, is 0. So average velocity is equal to 0 divided by 20, which is 0 meters per second. And that might strike you as odd. And one way to interpret that is, even though we were moving at this rate the entire time, this is telling us we ended up not going anywhere. So our average velocity for the trip was 0, which is basically a way of saying you went nowhere in terms of displacement, even though your car traveled a total distance of 20. So it's a subtle difference. We'll talk more about it later, but hopefully you feel comfortable enough with it as is. All right, so the next tutorial is gonna talk about more conceptual side of things. That will be another video.